The Stroboscope tutorial presents earth-moving operations for the construction of a dam. These operations use two kinds of loaders, the CAT 936E and the CAT 950E, and two types of tracks, the CAT 769C and the CAT 773B. These types of equipment are modeled as characterized resources starting in Model 6 of the tutorial. Model 6 of the tutorial is the first model to present a detailed earth moving using two types of loaders and two types of trucks. These equipment are modeled using characterized resources. The network for Model 6 is similar to the networks for the previous models and does not show the changes in the modeling of resources. These changes are made evident only if we look at the statements that describe the resources used by the model. The statements that define the various resources used in this model appear at the top of this list of statements. The statement card type loader defines a characterized resource of type loader that has the properties of bucket size, load variability, fixed load time, variable load time factor, and cost per hour. There are two subtypes defined for the characterized type loader, the S936E and the S950E. These are the two types of loaders used in these particular operations. Each one of these two subtypes is then followed by numbers that describe the particular values of their properties, such as bucket size, load variability, fixed load time, etc. These properties will be used later on to define other details of the earth-moving operations. The next characterized type is called truck. Truck has several properties such as capacity, empty weight, power, efficiency, retarding power, maximum speed, and several others that do not fit on this particular page. There are two subtypes defined for the characterized type truck. The first one is S769C and the second one is S773B. For each subtype again, we have numbers that follow the definition of subtypes that give us the specific values associated with the properties for the characterized type truck. For example, the capacity of the S769C is 23.6. These statements are then followed by the statement SaveProps that defines SaveProps for the characterized type truck. The SaveProps defined are called amount loaded, RR, and GR. Amount loaded is the amount of soil that is loaded into a truck and can be different for each particular instance of a truck at different points during the simulation. RR stands for rolling resistance, and it will be used to save the rolling resistance of the particular stretch of road that the truck happens to be on at that point in time. GR stands for grade, and it will be used to store the grade of the particular road that the truck happens to be on at that time. RR and GR will be used in engineering calculations to compute the speed of the truck. Model 6 does not use all the properties for the characterized resources loader and truck. Those properties will be used in Model 7. The next three statements define the process of drawing soil through link SL1. The first statement, draw until, ensures that trucks are loaded until they are within half of the loader's bucket of being full. This is to prevent loading the trucks beyond their capacity. The logical statement for the draw until attribute of link SL1 has two parts. The right-hand side part is the capacity of the truck currently residing in the new instance of load minus half of the bucket size of the loader in load. This gives us the minimum amount of soil that must be drawn through link SL1. The left-hand side of the inequality is the amount of soil in the current instance of load that has already been received by the starting instance of load. Draw until will continue until the count of soil in load increases to the point where it exceeds the right-hand side of this inequality. That is, the drawing process will continue until the truck is within one half of the loader's bucket of being full. The next statement, draw amount, specifies that the amount of soil drawn should be equal to the nominal size of the loader's bucket, which can be a big loader or a small loader, multiplied by random load variability. This is accomplished by taking the bucket size of the loader currently residing in the new instance of load that is starting up, multiplied by a normally distributed random variable with a mean of 1, whose standard deviation is the load variability of the loader currently residing in the new instance of load. The next statement, draw duration, describes the time it takes for the loader to place one bucket of soil into the truck. This time consists of a fixed component and a variable component that depends on how much soil is actually drawn by the bucket. The formula takes the fixed load time, which is a property of the loader in load, and adds to it the last amount drawn through link SL1 multiplied by the variable load time factor of the loader in load. Notice that fixed load time and variable load time factor are both properties of the loader currently residing in the new instance of load. Also notice that because the draw amount is a random quantity, it is necessary to use the property last amount drawn of link SL1 to refer to the actual amount of soil that was loaded by the bucket into the truck in this particular draw. Loading of soil will continue several times until the logical statement for the draw until statement becomes true, at which point drawing will stop. After that, Stroboscope will evaluate the expression for the duration of activity load. The duration of activity load consists of two parts. The first part is the time for the truck to maneuver into a loaded position, and the second part is the sum of the draw durations, which is the total time it took the loader to actually place the soil into the truck. The time to maneuver into loading position is given by the property maneuver of the truck currently residing in load. The sum of the draw durations is given by SL1.sum draw duration. These statements are sufficient to describe the creation of a new instance of activity load. When an instance of activity load terminates, it will release the loader back to loader's wait queue through link LD2, and it will release the truck through link TR2 to the subsequent instance of activity hold. It is important at this point that the truck know how much soil was loaded into it so that it will know how much soil to dump later on. Storing the amount of soil into a truck being released through TR2 is the most convenient way for the truck to remember how much soil it has received. This is accomplished by the statement ONRELEASE TR2. The action assign that occurs on release through the releasing link TR2 occurs while a truck is still inside the link TR2. At that point in time, the truck is being cursored by link TR2, and it is easy to assign to its SaveProp amount loaded the amount of soil that is currently in the terminating instance of load. That amount of soil is given by the variable load.soil.count. The result of the onReleased TR2 statement is to assign to the SaveProp amount loaded the amount of soil that the terminating instance of load had received through the link SL1. The next statement makes the duration of activity hold depend on the amount of soil that is actually loaded in the truck relative to the truck's capacity. This is accomplished by sampling a random variable from a normal distribution, multiplying it by the SaveProp amount loaded of the truck currently in activity hold, and dividing it by the property capacity of the truck that is currently in the instance of hold. When activity dump ends, it has to release an amount of soil through link SL2. The amount of soil released is given by the release amount statement for link SL2. That amount is given by the SaveProp amount loaded of the truck currently residing in the terminating instance of dump. For these statements to work as intended, it is very important that the links in the Stroboscope network be defined in the correct order. For the statements related to link SL1, it is necessary that we define first the link LD1 and then the link TR1. So the first resource drawn by a new instance of activity load would be the loader, and the second resource being drawn by a new instance of activity load would be a truck. This way, a new instance of activity load would contain a loader and a truck at the point in time that it draws through link SL1. Similarly, when activity dump terminates, it needs to know a property of the truck that is still in activity dump. For that to occur correctly, link SL2 must be defined first, and link TR4 must be defined after that. This way, the soil is released while the truck is still in the terminating of activity dump before it is released through link TR4. If these links are not defined in the appropriate order, Stroboscope will give a runtime error because it will not be able to access the properties of the resources being referenced in the various statements on this particular page. Model 7 is similar to Model 6 in that it uses characterized resources. In Model 7, activity hold is broken into two parts, hold to bridge and finish hold, and the return activity is broken into two parts, return to bridge and finish return. These activities have been broken up because on hold to bridge the trucks are going downhill, whereas in finish hold they're going uphill. Similarly, on return to bridge they're going downhill, whereas in finish return they're going uphill. Model 7 also introduces the queue spotter idle to model the fact that trucks cannot dump unless there is a spotter available to tell them exactly where to dump. Also, Model 7 introduces engineering calculations to calculate the durations of activities hold to bridge, finish hold, return to bridge, and finish return. The durations of these activities are calculated through the help of 4 VarProp properties that define formulas for the characterized resource truck. The first VarProp property for a truck is called EG, which stands for effective grade, and the formula for EG is RR plus GR. It is the sum of two SaveProps defined for a truck. SaveProps RR and GR will store the resistance properties of the various road segments. The VarProp EG will calculate the effective resistance, which is the sum of rolling resistance plus grade for the current segment of road that the truck is on. The next statement defines the VarProp effective power for a characterized resource of type truck. The formula for this VarProp is a conditional statement. If EG, the effective grade, is greater than 0, that means the truck is going uphill, in which case the effective power is the property power of the engine of the truck multiplied by the efficiency of its transmission. Otherwise, if the truck is going downhill, then the effective power is the retarding power property of the truck. The next VarProp defines the force that the engine has to overcome to move the truck up or down the grade. This VarProp is again defined for a resource type truck, and it has the name force. Its formula takes the empty weight property of the truck and adds to it the SaveProp amount loaded multiplied by soil density. The sum of these two amounts is then multiplied by the absolute value of the effective grade and then multiplied by 9.8 to turn the result into a force in newtons. The next VarProp defines the speed for the characterized type truck. The formula to calculate a truck's speed is to take the effective power of the engine and divide it by the force calculated by the previous VarProp. However, the result must not exceed the property maximum speed that each truck has. The result of the VarProp speed is the speed of the truck in meters per second. For these VarProp formulas to work as intended, it is necessary for each truck to know the rolling resistance and the grade for the road segment on which it is currently traveling. For example, when a truck is being released through link tier 2 to a new instance of haul to bridge, we can store into RR and GR the rolling resistance and the grade of the road from the load location to the bridge when the truck is going downhill. This is accomplished by the first two on-release statements for link tier 2. While the truck is still inside link tier 2, we assigned to the SaveProp RR the value 0.07 to show that the rolling resistance of the road from the load location to the bridge is 0.07 or 7%. Similarly, the second on-release statement assigns to the truck currently inside the link tier 2 the value negative 0.04, which is negative 4%, to the SaveProp GR of the truck. On release through tier 2, we also assigned to the SaveProp amount loaded the count of the soil in load, which is the amount of soil that was actually loaded in this particular truck. The VarProp statements defined up to here do not really do anything until they are used, and they are used in the duration statement that follows that describes the duration of the activity haul to bridge. The formula for this duration is to take the distance of the source to the bridge and divide it by the speed of the truck currently in the instance of the activity haul to bridge, and then divide the result by 60 to account for the transfer from seconds to minutes. The variable haul-to-bridge.truck.speed references the VarProp speed of the characterized truck that is currently inside the instance haul to bridge. The evaluation of this VarProp results in the evaluation of the formula for the VarProp speed. This VarProp references the VarProp effective power and the VarProp force. It also references the property max speed. The VarProp effective power references the VarProp effective grade, which in turn references the SaveProps RR and GR. The VarProp effective power also references the properties power, efficiency, and retarding power of the truck currently inside haul to bridge. This shows that a VarProp can reference other VarProps, and it can also reference SaveProps and other properties of the truck. The last statement defines the duration of activity dump. The duration of activity dump is given by the property dump time of the truck currently residing in the instance of dump that is starting up. Model 8 is similar to Model 7, but introduces the bridges that the trucks have to cross over the small river. This model uses a Type 1 bridge, which is a one-way bridge. The new nodes are haul wait for bridge, haul cross bridge, the queue bridges, the queue return wait for bridge, and the combi return cross bridge. The two combi activities, haul cross bridge and return cross bridge, represent the time it takes for a truck to traverse the one-way bridge. Notice that only one truck can be on the bridge at any given point in time. To model the bridges, we define three new variables. The first variable is the number of bridges. In this case, there is only one bridge. The second variable is the time it takes to cross a bridge, which is 1.75 minutes. The trucks have to go really slowly over the bridge to avoid excessive vibrations. The next variable, cost of a bridge, is simply the cost in dollars of that bridge. The bridge is modeled as a generic resource without any specific properties. This is done with the statement genType bridge. The queue bridges is initialized with the init statement init bridges number of bridges, which puts one bridge into the queue bridges. The duration of the two combi activities, haul cross bridge and return cross bridge, is the same, and it is defined to be the time to cross a bridge, which is 1.75 minutes. The variable total cost calculates the total cost of the entire model. Its formula takes the number of bridges and multiplies it by the cost of a bridge, and then adds to that the hourly cost of the operations multiplied by sim time in minutes and divided by 60 to turn minutes into hours. Model 8 allows only one truck to be on the bridge at any given point in time. Model 9 is similar to Model 8, but introduces additional nodes so that it can model bridges of Type 2. A Type 2 bridge allows multiple trucks to be on the bridge at the same time if they are traveling in the same direction. The distance between trucks traveling in the same direction has to be regulated so that they are not too close to each other. In this model, two trucks on a Type 2 bridge have to be separated by a distance of 0.3 minutes. To model this, the activity haul cross bridge is broken into two parts. The first part is still called whole cross bridge, and the second part is called whole cross bridge 2. The first part takes 0.3 minutes, and the second part takes the remainder, which is 1.45 minutes. Similarly, return cross bridge is also broken into two parts. Return cross bridge takes 0.3 minutes, and return cross bridge 2 takes the remainder 1.45 minutes. Consider the situation where we have one bridge of type 2. The queue bridges will be initialized with one resource. Combi whole cross bridge will be able to start if there is a bridge available and if there is a truck waiting in whole wait for bridge. If both queues are not empty, then whole cross bridge will be able to create an instance, take the bridge and then the truck, and then keep them for a duration of 0.3 minutes. At the end of that duration, the bridge will become free and go back to the queue bridges, and a new instance of whole cross bridge 2 will be created, and the truck will be passed on to that instance through link TR4A. If there is another truck waiting in the queue whole wait for bridge, then whole cross bridge will be able to start again. Again, it will take the bridge and the truck, create a new instance that takes 0.3 minutes, and then release the bridge and the truck after 0.3 minutes. The net effect is that the first truck crossing the bridge and the second truck crossing the bridge will have a distance between them, which is at least the duration of whole cross bridge, which happens to be 0.3 minutes. A similar situation occurs for trucks that are returning. The combi return cross bridge cannot start unless there is a bridge free in the bridge's queue and unless there is a truck waiting in the queue return wait for bridge. When those two conditions are satisfied, the combi return cross bridge will create an instance, and it will take the bridge and the truck from the queue return wait for bridge and keep them for 0.3 minutes. And at the end of that time, the bridge will be made free again, and it is possible for return cross bridge to create another instance. The obvious problem with this model is that it allows head-on collisions. This would occur if whole cross bridge terminates and starts whole cross bridge 2, releases the bridge, and this allows return cross bridge to start, in which case, while a hauling truck is finishing its traversal of the bridge, a returning truck begins entering the bridge, and the two trucks, the hauling truck and the returning truck, will collide head-on. The network itself does not show how this is prevented. For that, we have to look at the model statements. The first model statements for Model 9 are relatively simple to understand. At the beginning, we have three variables that define the number of bridges, the time to cross the bridge, and the time to enter the bridge. After that, we have a variable that defines the cost of a bridge. Type 2 bridges are more expensive than Type 1 bridges. After that, we have the duration of whole cross bridge and return cross bridge, which is the time to enter the bridge. After that, we have the duration of whole cross bridge 2 and return cross bridge 2, which is the time to cross the bridge, 1.75 minutes, minus the time to enter the bridge, which is 0.3 minutes. The important statements in this model are the last two that define the semaphores for activities whole cross bridge and return cross bridge. The formula for the first semaphore for activity whole cross bridge is the logical knot of the current instances of return cross bridge 2. This formula prevents whole cross bridge to be able to create an instance if there are any trucks finishing crossing the bridge in the returning direction. If there are any trucks that are on the bridge in the returning direction, then the current instances of return cross bridge 2 will be 1 or more. In that case, a logical NOT of the number of current instances will give us the number 0, which is a logical false. Thus, the semaphore for whole cross bridge will be false, and whole cross bridge will not be able to create an instance. Similarly, if there are any trucks finishing crossing the bridge in the hauling direction, then there will be current instances of whole cross bridge 2. If there are any current instances of whole cross bridge 2, then the logical NOT of that is the NOT of a number that is 1 or greater, which will give us a 0. A 0 is a logical false, and as a result, the semaphore of return cross bridge will be false, and the return cross bridge will not be able to start. The effect of these semaphores is that combi whole cross bridge cannot start if there is one more instance of return cross bridge 2 going on. Similarly, a return cross bridge cannot create an instance if there are any instances of whole cross bridge 2 going on. Thus, these two semaphores prevent head-on collisions by preventing trucks to enter the bridge if there are any trucks finishing crossing the bridge in the other direction. This page shows the output of running the simulation model for the 9th version of the tutorial. This printout is for a model that uses 2 Type 1 bridges. This is a situation where we have 2 bridges, each of which can hold 1 truck at the same time. The important results for this model are the total working time, which is 322 hours, followed by the total cost of the operation, which is $709,000. After that, we have the standard Stroboscope report that gives us statistics for the queues, activities, and the various characterized types and their subtypes. The statistics for characterized types give us information about their population, which is the current number of the population, the total population that ever existed, and then the average standard deviation minimum and maximum. They're all the same number because in this model we do not create or destroy any characterized resources. The next table gives us information about where these characterized resources spent their time. The resources are described as customers, and the nodes in which they spend time are described as hotels. As an example, consider the second row of this table. It shows that the truck subtype S769C spent the following time in the activity finish hall. The average truck of this subtype had 686 instances of finish hall. The total time that the average truck of this subtype spent in finish hall was 4,959 minutes. If we divide 4,959 by the total number of visits into that activity by the resource, we get the average visit time, which in this case is 7.22 minutes. So the average resource, on average, spent 7.22 minutes in an activity finish hall. The rest 3 numbers give us more statistics about the average visit time of the average resource. This output gives us the results for using one Type 2 bridge. This is the type of bridge that allows multiple trucks traveling in the same direction. The total working time is 340 hours, and the total cost is $712,000. It is interesting to notice that using one Type 2 bridge results in a longer project duration and a higher project cost. So clearly, using two Type 1 bridges is a better alternative. The final page for the Stroboscope tutorial summarizes the results of the various models and of using various numbers of the two types of bridges. The first table shows the results for the first 7 models that do not include modeling the bridges. The costs for these models are very close, as they should be, because they are essentially alternative ways of modeling the same operations. The next 3 tables investigate using 1 or 2 or 3 Type 1 bridges. For each possibility, the tables show the results of multiple replications. The first table and the last table show 3 replications. The table for using 2 Type 1 bridges shows 10 replications. It is clear from these results that using 2 Type 1 bridges is better than using 1 or 3 Type 1 bridges. The average cost is about $710,000, which is substantially less than the cost of using one Type 1 bridge, which is about $800,000, and the cost of using 3 Type 1 bridges, which is again about $800,000. So using 2 Type 1 bridges results in savings of about $100,000. The next 2 tables show the results for using one Type 2 bridge and using 2 Type 2 bridges. Again, it is clear that using one Type 2 bridge is better than using 2 Type 2 bridges because the cost is about $150,000 less, $715,000 relative to $870,000. Comparing the alternatives of using 2 Type 1 bridges versus using one Type 2 bridge, the costs are very close. Nevertheless, using 2 Type 1 bridges is less expensive at $710,000 relative to $715,000. It is possible to do additional analysis and investigate other possibilities.